This project was requested by the OSU Department of Rangeland Ecology. They wish to replace the existing loggers they have with newer, more efficient models. Currently, the loggers they have do not have a long enough battery life, and with the technological upgrades over the last few years, our design will be much more efficient and will be able to last longer using generic D-cell batteries, as opposed to the medical-grade batteries they have to use currently for long-term tracking. The client plans to use them for tracking cattle, although if the design works well, we will be also able to attach them to other animals to track their movements as well. There are already some GPS data loggers out there, some which are for general public use, but can only last for a day or a couple days at most. There are also scientific loggers that are built to log for months at a time, but they are far too expensive. Our design will be around the same price as some of the general use GPS loggers, but the time it can log for will be much closer to the lifetime of the scientific loggers. It will be a product specifically built for our customer to meet their specific needs for tracking their animals. We chose this project because we felt that it would be a good fit for all of our skills. The systems were already set up in a way where each of us could play to our strengths. It was also an interesting project idea. The idea of working with GPS interested all of us as well. The rest of this presentation will be broken up into the following sections: customer and engineering requirements, block diagram analysis, and unique design concerns. One customer requirement is that the logger should be deployable for periods of 6 months, which is about how long their current version can go with medical grade batteries. The related engineering requirements are as follows. The data logger will not consume more than 200 milliwatts when logging data. The data logger will not consume more than 50 milliwatts when in sleep mode. The logger will be able to support a micro SD card of at least 8 gigabytes. The efficiency of the logger's power regulation system will be at least 60% when in logging mode. Another customer requirement is that the device will log location data from a global navigation satellite system. The related engineering requirements are as follows. The data logger will output coordinates that are accurate to within 20 meters from a known location on campus. The final product will have the ability to log at frequencies of up to 1 Hz.
One of our customer requirements is the logger will be powered by a battery pack consisting of the 40-cell batteries, so our customer could still keep using the batteries that they left. The engineering requirements related on these customer requirements are the follows. The data logger will not consume more than 200 milliwatts when logging the data. The data logger will not consume more than 50 milliwatts when in the sleep model. The data logger will work on the power supply voltage ranging from the 1.8 volts to the 4.5 volts. The logger will not draw more than 1 ampere when supplied by the power source consisting of the 40-cell batteries connected in parallel. Also, our customer required logged data will be stored on the micro SD card in the format that the user can easily to access. The engineering requirements related on these customer requirements are the follows. The logger will be able to handle a 10-second power interruption without logging data and losing data that has previously been stored on the micro SD card. There will be a 3.3 volts DC rail compactor of the supplying 200 milliamperes interruption to the device. The logger will be able to supply a micro SD card at least 8 kilobits. The logger will implement a Windows readable file system for the writing data to the micro SD card.
The logger also needs to fit into pre-existing containers provided by the Department of Rangeland Ecology. So the PCB will be no larger than 5 centimeters by 5 centimeters by 2 centimeters. The logger should also be able to add sensors on daughter boards with no hardware changes and minimal software changes. So the logger will provide a 3.3 volt output pin, plus or minus 100 millivolts, capable of supplying 100 milliamps of current. Also, the logger will provide 2 pins capable of supporting I2C communication with the daughter board.
The power regulation block receives power from the battery pack, which will be 2 to 7 volts, depending on how the batteries are aligned, and it will change over time. We are currently planning to use an alignment of setting 2 batteries in series and putting another 2 in parallel with the first set in order to create a typical voltage of roughly 3 volts. With this new voltage set point, it was much easier to find power regulators that would fit the input voltage. We need 2 regulators for separate rails, a 3.3 volt rail and a 1.8 volt rail. The 1.8 volt rail will be for the microcontroller and possibly the GPS receiver. The 3.3 volt rail will be for the SD card and the other future applications which will be using I2C. The regulator we have currently decided on for the 3.3 volt line is from the TPS6303X family. It has an acceptable efficiency for low power usage, which we'll be using for the majority of the time. This one was selected over one from Linear Technology, the LTC3525D-3.3, which is slightly better efficiency at low power, but the output current for the Linear Technology one was a little too close for our required current limit. The regulator for the 1.8 volt rail we have currently chosen is from the TPS6620X family. It has an appropriate output current, and the power efficiency is sufficiently high at low powers, which will be running at the majority of the time.
Now, I would like to introduce our communication system in our project. There are 4 different parts in our communication system: GPS receiver, microcontroller, micro SD card, and also the dot board. The programmer will write the code for the microcontroller, so the microcontroller could lead all the communications between the different components. Since the GPS receiver gets a signal from the outside, the microcontroller will ask for the GPS receiver transfer that signal to the digital data, and the GPS receiver will transfer that data to the microcontroller. After doing that, the microcontroller will send a 1.8 volts signal, which we call SPI low, to the level shifter, and coming out with a 3.3 volts signal, which we call SPI high, to the micro SD card. So under the 3.3 volts, the micro SD card could be storing the data. The communication between the dot board and the microcontroller is same as the communication between the micro SD card and the microcontroller.
Now we'll spend a few minutes talking about the GPS receiver. The GPS receiver is an important piece of the overall logger system. Since the Department of Rangeland Ecology plans on using these devices to track animals all around the world, the loggers need to be able to receive GPS signals in a variety of environments. To accomplish this, both the antenna and the receiver that we choose will need to be capable of tracking the location of the animal in harsh conditions. The GPS receiver is one of the power-hungriest components in the data logger, and as such, it is very important to select an energy-efficient receiver module. However, decreased power consumption typically leads to decreased performance. Therefore, when choosing a GPS receiver, a balance had to be found between energy efficiency and performance. Many manufacturers are now producing GPS modules that are capable of receiving both GPS and GLONASS signals. Due to the increased number of satellites that can be observed, these receivers have a better chance of finding a fix and are generally more accurate than receivers that can only pick up GPS signals. As was stated before, increases in performance often come at the price of reduced energy efficiency. The combined GPS GLONASS receivers are no exception to this trend, and most dual-function modules consume significantly more power than their GPS-only counterparts. The module that we have tentatively selected for this project is the Neo6 from uBlocks. This is one of the most energy-efficient receivers on the market and comes from a manufacturer with a great reputation. While the Neo6 can only receive GPS signals, the next generation module, the Neo7, is also capable of receiving GLONASS signals. The Neo7 is a drop-in compatible with the Neo6, so in the future, the Department of Rangeland Ecology will have the option to upgrade the module to the Neo7 with relative ease. In summary, because our customer wants these devices to be able to run for periods of many months on power sources of just 4 D-cell batteries, power efficiency is something we've needed to consider for every block in the system. We've made an effort to pick components that are both highly power efficient and capable of performing in a variety of environments around the world. Now, not all aspects of our design could be addressed in this brief presentation, but we hope to have given you a good idea of the top-level workings of our design. In the end, we hope to provide the Department of Rangeland Ecology with a data logger that not only meets their requirements, but allows them to track wildlife in ways that they cannot do with their current equipment.